Graphite is actually a hexagonal structure of several layers stacked on top of each other. A representative diagram is shown here in the black, and you see that in one plane or in 2 dimensions, there are 6 carbon atoms arranged in a hexagon. So that gives a atomic plane, atomic layer. And there are several of these. You can see at the bottom where it says stack of layers, it's there. And you see several of these layers are sitting on top of each other. The carbon-carbon bond has a length of about something like D, which is written in the red here. So the interlayer spacing is 2.5 D. That's the geometrical configuration it must have to remain in a stable equilibrium. Now you would wonder, because carbon had 4 unpaired electrons, and each of these bonding that we see here is only 3. What happened to the 4th electron? The 4th electron actually does the miracle for this material. Because it has no binding possibility with any neighboring atom, it behaves like a free electron, and we call it, in the language of graphene science, it's called a delocalized electron. And the delocalized electron, because it's not required for any binding purposes, it can roam around on the lattice freely. So if we apply a voltage between the 2 ends of the graphite, then the electrons will move, giving a current to it. Now each layer of this, what we have shown here, is what is called a graphene. And the stack of these layers together is what is called a graphite. So when you naturally see graphite, we actually see a stack of the graphene. Graphenes are 2-dimensional hexagonal structures, monoatomic layer of carbon. Now the stacks are held together with each other. There must be some binding energy, otherwise they will slip away. The binding energy is a van der Waals interaction. What is the origin of that? Origin is when the electrons are free in each layer, they keep on moving there in the zigzag motion, trying to explore all the space. Same thing happening in all the layers. During the process, the dipoles are formed in each of the layers, and the induced dipoles are formed in the neighboring layers. And then there is dipole-dipole interaction, giving rise to van der Waals dispersion forces. And that is what holds this thing together. But again, realize that van der Waals forces are not very strong. So the layers can slip against each other with very little energy. We can slide them against each other. Imagine like a pack of playing cards. Each card is strong enough, but if you stack 52 of them, you can slide each of them over the neighboring or lower or upper one, because there is no binding between the two. It's something like this here, very poorly bound. So therefore, it can slide, the layers can slide against each other. Second thing is, the electrons that I talked about, they roam around in only one 2D plane, in one plane. It doesn't go to the next plane or the other one. So it is confined to that plane. All the motion is confined to that plane. Okay. Now, because of this, the flexibility of this material, this can be utilized and explored more for making nanomaterials out of this thing.
NSTC is again organizing the workshops on very exciting topics. Registration link is given in the description box below. So book your seat as per your availability and interest. For more updates, subscribe to our channel. Click the links shown on the screen to stay connected.